Hello everyone, my name is Ludovico Lami. This is the extended talk for the Beyond IID 8 conference in 2020, November 2020. Okay, so I'm at the University of Ulm, yes, and also funded by Alexander von Humboldt Foundation. Okay, so today I want to talk to you about this paper that we recently put on the archive, and well, actually it has been already published in PRL, Bosonic quantum communication across arbitrarily high loss channels. And the informal name is die-hard quantum communication for reasons that will become apparent immediately. So, okay, I thank my co-authors, without whom this would not have been possible, Martin Plenio, Vittorio Giovannitti, and Alexander Olevo. Okay, so this is a brief outline of what I'm going to talk to you about. First of all, a little bit of introduction on continuous variable quantum systems and on the general theory of quantum communication. Then I will present a very well known in the community mathematical model for quantum communication across optical fibers, and something that is known as a general attenuator channel. Then we will look at the special case where the transmissivity is 1/2, and we'll see what we can say for that special case. Lastly, but most importantly, we will look at a scheme called a passive environment assistance for increasing quantum communication. And we will look in particular at what happens when the transmissivity of the channel is arbitrarily small. Okay, so first of all, continuous variable quantum systems. So they are just finite number. There's just a finite number of harmonic oscillators, quantum harmonic oscillators. Okay, this is just what a continuous variable quantum system will be for me. So a quantum harmonic oscillator, you know more or less what it is, I guess. For those of you who don't know, it's basically a particle in a line with a harmonic potential that is a parabolic potential. Okay, and what it turns out is that there is an infinite set of energy levels with increasing energy all the way from a constant, and they are equally spaced all the way from a constant to infinity. Okay, so if you want to describe this mathematically, you start with a Hilbert space, and the Hilbert space is just L2 of R to the power of the number of modes that you have there. So if you have one mode, this would be just L2 over R. So L2 is the set of the Hilbert space of square integrable functions over R. Okay, so Rm and square integrable functions over Rn. Okay, so and quantum states are just density operators, that is trace class operators on those Hilbert space, that they're positive semi-definite and they have trace 1. Okay, and for this special case of the harmonic oscillator, we have also special operators. They're called creation and annihilation operators, and they obey some special commutation relations that are called canonical commutation relations that are like this. So the commutator between AJ and AK dagger must be a multiple of the identity. If J is different from K, it will be downright 0. But if J is equal to K, this will be just the identity. This is the identity operator of the Hilbert space. This is Hilbert space. Okay, in terms of those, you can construct Fock states that are exactly these energy levels, and they are defined, say, for a single system. So I have no index here because it's just a single mode. You apply to the vacuum state, which is a special state, which would be the ground state of this Hamiltonian. You apply the creation operator k times, and then normalize the resulting state. Okay, so another very important object that we can construct is a displacement operator. Displacement operator will be something like this. It's the exponential of a linear form in the creation and annihilation operators. Okay, so this Zj will be a vector of complex numbers. Okay, so these are unitary operators that are like isometries of the Hilbert space, actually unitary operators, so they're even surjective. And in terms of those, you can construct what is called a characteristic function. You have this bunch of unitary operators, and you take the trace of your state rho against all of those. And this will be a function defined on C to the n. And so the important thing is that this characteristic functions, these quantum characteristic functions, are in one-to-one correspondence with quantum states. Okay, so that means that you can reconstruct the state in terms of the characteristic function, and of course vice versa. So there are no two states with the same characteristic function in particular, two distinct states with the same characteristic function. Okay. So that also means that whenever you want to describe a transformation between states, you can describe it equivalently in terms of transformation between characteristic functions. Okay, right. Okay, so now what are general attenuator channels? Okay, so what we want to model is a quantum communication across a physical medium, typically with light, okay? Because quantum light is modeled by a continuous variable quantum system. Okay, so the two typical physical media that we want to communicate across are optical fibers. These are optical fibers, and well, and air, right, or space. So like Earth to satellite communication, and vice versa, satellite to Earth. And of course, Earth to Earth mediated by a satellite. Okay, so we have to find a reasonable mathematical model for this physical process. So what happens there is that you send a channel across an optical fiber, and the optical fiber is very long, and a lot of things can happen along the way. For instance, your signal, some of the photons can get lost, can interact with the optical fiber, the material that composes the optical fiber get absorbed, or just get lost, so escape the guide, the optical guide, right? So, and we model this mathematically with an interaction, a unitary interaction with an environment. Okay, right. So a very reasonable mathematical model for this is a beam splitter. So let's say that your signal state rho is sent across a beam splitter and is mixed in a beam splitter with an environment state. So a beam splitter is just a semi-reflective mirror. So this will let your signal pass for some fraction, and will also reflect some of the environment state with some other fraction. So your output state will be kind of a mixture, in some sense, of your state and the environment state. Okay, so the noisier the environment, and the smaller the transmissivity, the noisier the state. So the transmissivity is kind of how much of your original state gets sent through. Okay, is sent through without disturbance. So smaller transmissivity means that the channel is more noisy and will introduce more environmental noise over here. Vice versa, high transmissivity means that you're getting a good signal, which is not very noisy. Okay, so we want to model this mathematically. We represent this by a quantum channel, and the quantum channel works like this. You take the input state, you tensor it with the environment state, then you apply the unitary that represents this beam splitter transformation. Okay, and it turns out this is actually the unitary. This A is the annihilation operator for the first mode, and this B is the annihilation operator for the second mode. Okay, so this is a unitary operation, and this will be kind of the angle by which you mix the two modes. So you kind of perform a rotation with the objective of mixing the two modes. Okay, and as I said before, we can equivalently describe this process in terms of characteristic functions. Okay, and the transformation looks like this. You start from a characteristic function, and then the one at the output will be the product, the rescaled product of the two characteristic functions of the input state and of the environment state. Right. Okay, so what we want to do here is to maximize the quantum capacity. So what this means is we want to maximize the ultimate rate of quantum communication. Okay, so now we have to pause a little to try and understand what this means exactly. Okay, so we want to use basically a channel N, okay, a generic channel, and we will focus on general attenuators later on. But in general, we want to use a channel N to simulate the noiseless channel. Okay, so we want to use many instances of this channel to simulate noiseless channels. Okay, so what this means is that you want to transmit Rn qubits. Okay, so this will denote the integer part. Okay, so whatever. So you have a number of qubits, which is typically very large. N is very large, and R will be some rate of communication larger than 0. Okay, so you perform an encoding. That means a transformations that maps this Rn qubits into n copies of the input system of n. Then you apply n times the channel n to each of those. And then you perform a decoding operation, which will be another quantum channel, and the output will be exactly the same as the original input. that is Rn qubits. And we want this global transformation to be really close to a noiseless channel. That is just channel where you input the state and just the output is the same as the input. So you just send it all the way to Bob, to the party on the other side of, say, the ocean, whatever, without any noise. Okay, and so if this simulation, because this is a simulation, we are using n copies of a channel n to simulate Rn copies of a noiseless qubit channel. If this simulation is possible for all n, with the error here that I'm not going to explain in too much detail, but it's the error in the transmission, basically the worst case error in the transmission. If the error goes to 0 and still the simulation is possible with this very good, very small error that even goes to 0 as n goes to infinity, the rate R is said to be achievable. And the quantum capacity is just the supremum of all achievable rates for this simulation task. Okay, so and luckily enough, there is a theorem by Lloyd, Shor, and Devetak, very famous one, LSD, that provides a formula to at least in principle compute the quantum capacity. And it's a complicated formula, unfortunately. So it all starts with computing this Q1 quantity. So this Q1 quantity, you start by taking a state, bipartite state. So say from A, so this will be a pure state between A and a local register on Alice's side. Let's call it A prime. And then you send the A half of the state through the channel, and you get a state from Alice, A prime, and Bob, B. And then you compute what is called the coherent information of that state. The coherent information will just be the entropy, the von Neumann entropy of the B system minus the global von Neumann entropy of the whole state. Okay, this is the explicit formula. And so unfortunately, okay, so this is a complicated optimization in principle, but it's still a single letter. So it's just a single optimization for a channel. This is a finite dimensional channel, say, finite dimensional input and finite dimensional output. So this will be a pure state in a finite dimensional system, and that's, in principle, it's manageable, at least numerically. But the bad news here is that you also require regularization. That is, you require that you compute this Q1 not for the channel n, but for the channel n to some tensor power. And then you have to regularize. Okay, so, and what happens is that also if the input dimension of the channel is infinite, so it could be that you can send an infinite amount of quantum information with just one instance of the channel, because of course the input dimension is infinite. So if the channel is not noisy, so if the channel is the identity, then you can send actually an infinite amount of information with just one use. Okay, so this is, of course, it's a kind of a spurious phenomenon that is due to the fact that the input dimension is infinite, as I said. So, but usually infinities are kind of hidden away in physics, right? And the reason why this is so in this case is because most infinite dimensional systems, for example, the continuous variable quantum systems that we saw before, those have come with a Hamiltonian. So a Hamiltonian that dictates that if you want to explore all infinite dimensions of the space, you need to increase your energy budget. So if you have to prepare higher energy states if you want to explore the whole Hilbert space. And this is the reason why it's very useful to impose an energy constraint and to talk about energy constrained quantum capacity. What does it mean? Well, it just means that we go back to the scheme before, and we just say, yeah, okay, whatever the input state here after the encoding, the input state of the channel, I do not allow this to have an unbounded amount of energy, but I require instead that the sum of the energy, that the energy of the state, basically, where the Hamiltonian is just the sum of the Hamiltonians on the input systems of n, because yeah, this is, I didn't say it before, but so let's say that we fix a Hamiltonian on the input system of the channel n. Let's call it HA. Okay, so and the total energy of this with respect to the sum Hamiltonian, okay, so no interaction terms, must be less than a constant times the number of uses of the channel. Okay, so we allow this energy to blow up as n goes to infinity, but the average energy per use of the channel must be fixed. So this E is a fixed number, okay? And the energy constraint quantum capacity will depend on this number, and also on the Hamiltonian, of course. And this is defined as usual as the supremum of all achievable rates with this energy constraint. Right. Okay, so, and also in this case, you get a LSD kind of theorem. It's called an energy constraint LSD theorem. I recommend reading the paper by Mark Wilde and Key for this result, for a proof of this result. Okay, so it works like before. You compute first this Q1 quantity with the energy constraint, and it's the same as this, the maximum coherent information between input and output, well, between Alice and Bob. But you require that the pure state that you use has energy, local energy on A, which is at most E. Okay, and the Hamiltonian on n copies is just the sum Hamiltonian as before, no interaction terms. And you regularize, you compute the Q1 for the n tensor n channel. Right. Okay, so, well, it turns out that, of course, the larger the energy, the more space, the more room you have in your Hilbert space to do the encoding, and the better. So the higher the quantum capacity, okay? So for every fixed energy E, well, the quantum capacity without energy constraint is, of course, larger than the one with the energy constraint. Okay, so what happens for general attenuators, right? Okay, so for general attenuators, there is a very natural Hamiltonian on the input, which is just the total photon number. Total photon number is expressed in this way in terms of the creation and annihilation operators. Okay, so it just counts the levels of the harmonic oscillator, right? Okay, typically we will have one system, one mode system on the input and also on the output, of course. So then the Hamiltonian is simply the number operator, A daga A. Okay, this will be 0 for the vacuum and K for any kth Fock state. Okay, so to talk about quantum capacity, okay, we have fixed the Hamiltonian. We need also to say something about the state. Okay, so the two most well-studied state are the thermal state. This is just the thermal state, so the Gibbs state for this Hamiltonian. And so if you actually write it down, it looks like this, where n is the average energy, average photon number of the state. And so in that case, you get a thermal attenuator. And the other important case is the vacuum, where you get here the vacuum, which is just the thermal state with 0 temperature, so 0 mean photon number. And in that case, you get an even simpler channel, which is called the pure loss channel. Okay, so it turns out we don't have an exact formula for the energy constraint quantum capacity of the thermal attenuator, but we do have one for the energy constraint quantum capacity of the pure loss channel. Okay, so, and well, it turns out, okay, it's a formula like this. You can plot it. This is the plot for different values of the average input energy, right? So of course it grows with the higher the energy, the higher the capacity, and it reaches a limit value, which is like this for infinity, okay? Okay, so the problem there is that for sigma, when either sigma is the vacuum or is the thermal state, it happens that all quantum capacities vanish when lambda is smaller than 1/2. And okay, this is not entirely surprising because when lambda is very small, you are sending basically your output state will be made more of the environment and less of your noise and less of your signal state, okay? So there is more noise than actual signal. So in that sense, it's not so surprising that you cannot do perfect communication. Okay, so the problem is that okay, transmissivity below 1/2 it happens quite quickly if you deploy a long optical fiber, because so that the average transmissivity coefficient is like this. So basically it's 0.2 decibel per kilometer. So that means that every 5 kilometers you make 1 decibel of attenuation. So that means every 5 times 10 kilometers, so 50 kilometers, you make 10 decibel of attenuation. That is a factor of 10. Okay, so this is the formula of the capacity of the transmissivity for typical optical fiber, commercial optical fibers, but even very sophisticated ones cannot cannot do much better than this. So that means that you will have a zero quantum capacity for larger than for L larger than 15 kilometers. Okay, so that's not very good if you want to deploy long optical fibers. And yeah, okay, so the question is how general this phenomenon is. So this phenomenon of vanishing quantum capacity for lambda smaller than 1/2. And the related question is whether we can keep the quantum capacity away from zero for lambda smaller than 1/2. And of course, like to do this, we have to choose sigma carefully, because if we choose sigma kind of recklessly, we can pick the vacuum and then the quantum capacity vanishes. But if we modify, if you choose the environmental noise carefully, then maybe this does not happen anymore. Okay, so a partial answer to this phenomenon, to this question one is okay, we start looking at the special point 1/2, okay, where we know that quantum capacity vanishes for the thermal attenuator. And it turns out that this does not only happen when sigma is a thermal state, but it happens when sigma is a much more general state of this form. So this will be this is a probability distribution. So we're taking a probability, we're taking a convex mixture of a family of states, and these are displaced states. And so this is a displacement operator with amount z. And this state here that we are displacing, this can also depend on z, but we require that this is symmetric under phase space inversion for all z. Okay, so what is the phase space inversion? So it's just -1 to the total photon number. Okay, so this is in phase space. For those of you who know the phase space picture, this amounts to exactly a geometric inversion with respect to the origin in phase space. So sending a vector to minus the same vector. Okay, so when sigma is of this form, then the channel with transmissivity 1/2, the general attenuator with transmissivity 1/2 and environmental state sigma is anti-degradable, whatever that means that I haven't defined. But for those of you who know, it's anti-degradable. And in particular, this is what we really care about, the quantum capacity is 0, even without the energy constraint. So it's just impossible, even if you allow for infinite energy states, to communicate quantumly. Okay. And okay, so how general is this? Well, okay, states that can be written like this, and so to which the theorem applies, include, for instance, all convex combinations of Gaussian states and all, say, Fock diagonal states, because this is again, it's invariant on the phase space inversion because it picks up just the phase. So this vanishes when you take this ket bra. And so that means that this is it's exactly a convex combination of this form, actually, without even the probability distribution. So this would be trivial. And so z is equal to 0. So for a vast class of states, convex combinations of Gaussian states, Fock diagonal states, in particular, or what I call classical states, so convex combinations of coherent states, for all of those, the quantum capacity vanishes at the special point 1/2. And okay, so this is I mean, this is not a complete general phenomenon in the sense that if you pick the right state sigma that is not of this form, then the quantum capacity can stay above 0, and even with an energy constraint. Okay, so here is a simple example. And okay, so just take sigma to be the stupidest thing that you could take that is not of this form. So just a superposition of 0 and 1. And if you pick the right state for the transmission, so in the LSD theorem, there is the supremum. If you pick the right state psi here, which I wrote down here, well, it turns out that the coherent information is positive. Okay, so that you get a positive quantum capacity. And this is the plot, and okay, fine. Okay, you get a small but positive quantum capacity. And this gives us plenty of examples where this quantum capacity of general attenuators for the special point 1/2 is positive. Okay, so this could be not so surprising. In the end, we are just amending this special feature of the attenuator, of the thermal attenuator, by just healing this special point 1/2 by picking an environmental state that is more coherent. This could not come as a surprise, but still, it begs the question whether, well, this holds just for the special point 1/2, or maybe all the way up to a threshold, or it holds all the way down to 0. So when transmissivity is very small also. Okay, so to explain why we care about this, let me just make a brief detour and talk about what is called a passive environment assisted quantum capacity. Okay, so the concept has been laid out in this beautiful paper by Karumanchi et al. A few years ago. So the basic idea, so I won't go into the scheme and the fully general scheme, because this is it's much more general than we actually need. But I recommend reading the paper. It's very, very beautiful. But so the basic idea is that we allow a benevolent helper to control the environment state in the quantum channel. Okay, so you start with a channel from a system by Alice and the environment to Bob. And this encodes kind of an interaction between the two. Okay, so a way of sending the message. And then you try and optimize the quantum capacity by saying, yeah, okay, the benevolent helper picks the best possible environment state here so as to maximize the capacity of this channel. So this is a channel now from Alice to Bob, and the benevolent helper wants to make them very capable of communicating very well, right? So to maximize the quantum capacity. Okay, so and this could be could look like a bit a contrived scheme, because of course in general the environmental noise is not a person or it's just the environment, right? So it's just a natural phenomena that leaks and stuff that affect your transmission. So it can be benevolent in a way, right? But okay, so but this is not so true, because for instance you could imagine affecting the environment state, and this can happen, for instance, when you have channels that are not memoryless. So for instance, Alice could start by sending a strong pulse across the channel. So what this strong pulse does is it doesn't communicate anything to Bob. There is no information, so Bob just discards it, but it excites the environment state in a suitable state. So it modifies the state of the environment through this interaction and makes it something different, something that now we can use to transmit the actual information. So now Alice sends the actual information and she has affected this environment state. So maybe she has done so in a way that improves the quantum capacity. Okay, so of course, I mean, there are several ways Alice could do this. And it's not clear that she can actually reach every possible state of the environment, but for the sake of the argument, let's say that she can. So she can affect the environment in any way she wants, right? So just as to benchmark the ultimate kind of performance of this passive environment assisted scheme. Okay, so in our case, we start with a channel, and well, okay, I mean the Hamiltonian, the interaction there is dictated by the beam splitter unitary, right? So this is the channel. So okay, so then when Eve chooses her quantum state, basically you are defining a channel between Alice and Bob that is a general attenuator. Okay, so you maximize the quantum capacity, say energy constraint, of the general attenuator over all possible choices of the state of Eve. And in this way, since you are eliminating the dependence on the sigma by taking this supremum, you get just a function of the transmissivity lambda and of the energy E. And this function is an interesting object, and it's we are interested in studying this function theta and to see what its behavior with respect to lambda is. Okay, so because usually we fix an energy E, say E equal to 1, and we want to study what the behavior with respect to lambda is. Okay, so we already know that this theta is, of course, it's positive for all lambda larger than 1/2 and all positive E, because we can just take the pure loss channel. So we just take, we just have Eve input the vacuum state there, and there you get a positive quantum capacity. Okay, so that's not very interesting. We're just reviewing what we already know. Okay, so from now on, as I said, we fix a small value of E. Say, actually, we just need E equal to 1/2, whatever. Yes, so in particular, what is the value of lambda of theta when lambda becomes very small? Okay, so for lambda smaller than 1/2 and also for lambda going to 0. So is there a threshold value below which the quantum capacity vanishes for all thermal attenuators, for all general attenuators. So it means that the function theta itself vanishes. Okay, so we expect the function to be a kind of zero below a certain threshold value. Okay, so, and the main theorem that we prove is that this is actually not the case. In fact, it's actually the opposite, that the function theta stays positive, actually larger than a constant, fixed constant for all lambda that are strictly positive. So it just becomes zero when lambda is equal to zero. Of course, then you don't communicate anything, so you cannot hope to have any quantum capacity. But if lambda is very small, even one in a millionth, there is a state sigma that you can input in the environmental modes that makes your quantum capacity larger than a constant. Okay, so that is independent of lambda. That's quite surprising, at least to me, it was quite surprising. And let me present some of the reasons why this is surprising. Okay, so this is why, I mean, of course, this is the reason why the nickname of the paper, Die Hard Quantum Communication, because you are not able to kill the quantum communication even when the transmissivity is very small, if you allow a benevolent helper to play their role, okay? And this is true even when you fix the input energy. So you are just, well, okay, one could think, yeah, okay, the transmissivity is small, but here I have a very large Hilbert space, so I can access a very large range of possibilities. So, okay, maybe I can make up for the small transmissivity by going to, some remote corner of the Hilbert space. No, this is not what's going on here, because you are fixing also the input energy. Okay, so that means you have actually a small Hilbert space, kind of a small section of the Hilbert space to play with, but still you can achieve non-zero quantum capacity and larger than a constant. And this also implies that since your energy here is fixed and transmissivity is small, actually the energy at the output system comes overwhelmingly from the environment. And just a very small fraction comes from your state. Okay, because it turns out that the energy of this one actually blows up. So the energy of the environment state needed to have positive quantum capacity is very large. So that means that here you get a state that is very bright, and almost all of the photons come from the environment, and just very few from your state. But still, you're able to filter this out, to filter all noise out, and to recover a non-zero quantum communication. And that, to me, it was quite surprising. And it is, I mean, ultimately, it is very surprising. Okay, yeah, so it turns out that actually your state can be actually a Fock state. So if lambda is, okay, sufficiently small, say below 1/3, below 1/2, actually, it's already enough, you can take this to be a Fock state. So that means that the energy of this grows when lambda, because this n will grow when lambda goes to 0. So the energy of the environment blows up. And so another important consequence is that, so, okay, note that this state, as I said before, is invariant under phase space inversion. You remember this good old phase space inversion, which is -1 to the total photon number. It's invariant because this state picks just a phase. So when you take the cat bra, this vanishes. And so that means that the quantum capacity at the special point 1/2 vanishes. So you have this this very peculiar feature that for lambda smaller, sufficiently small, the quantum capacity is positive and larger than a constant. But for when lambda is larger, 1/2, so you have better transmissivity, you get 0 quantum capacity. And that's really curious. So that means that the quantum capacity, so that there are states, particularly the Fock state, for which this quantum capacity of this general attenuator as a function of lambda is not monotonic, because it is positive for some lambda smaller than 1/2, and it is 0 for lambda equal 1/2. And that's really, yeah, surprising. And it's, of course, it's infinity for lambda is equal to 1, because then you have perfect transmission. So this quantum capacity is not monotonic in lambda. That's really kind of a curious phenomenon. I mean, it's actually, if you really think about this, there is no reason why this shouldn't happen. But it's still intuitively a bit surprising, at least to me, that you can have a channel where a smaller transmissivity actually helps quantum communication. And that's yeah, quite peculiar. Okay, so and the other question that this whole theorem begs, very natural, is what can we say about this constant? Okay, so the good news is that the proof is not just it gives you an explicit value of the constant. It's not just an implicit construction, but it actually gives you estimates for this constant. Okay, and the bad news is that this actually is very small. The estimate that we get is very small. Is this ridiculously small number. But actually, I mean, numerical estimates suggest that this is actually much larger. I mean, this is just that our proof is not very good in this respect, and this you can actually make this very larger, of the order of a few percent. And the good thing is that actually, if you consider just say the limit when lambda goes to 0, okay, so exclude the 0.1/2 and all, which is actually the problematic one that makes this one smaller. If you just consider sufficiently small lambda, this modified C that just works for small lambda, we can actually prove that this is much larger. So this is the actual value that we lower bound that we get for smaller lambda, and that's yeah. So I mean, you get a 2% of so basically you get 2 bits per 100 uses of the channel. Okay, which is again, this is the numeric suggests that this is actually much larger than this. This is just the proof that gives you a bad estimate. Okay, so let me briefly talk about the proof idea, because it's stupidly simple, and the technical bit is just the last step. Okay, so you'll see that the idea is just the simplest idea you could have, but then to make it work, you actually need to prove something. Okay, so the first thing is right. I mean, we want, so let's say we stick to small lambda. Okay, so lambda smaller than 1/3, because this is lambda going to 0 seems to be really the problematic part, the heart of the problem. And okay, the other part, the other points, you can kind of get away with patching up other solutions that we already saw. Actually, around the 0.1/2, we already saw how to get a positive quantum capacity, and yeah, so that gives you a solution, so a lower bound for theta when lambda is around 1/2. Okay, so here we are considering, okay, the energy constraint is 1/2, as I said before. Okay, so the LSD theorem tells you that, okay, if you want to lower bound this, which is you just pick a clever state sigma, and then for a choice of state sigma, you have to also pick a state transmission state, and you have to compute the coherent information at the output between Alice and Bob on the output state of the channel. And also here we have an energy constraint on the reduced state on A. Okay, so yeah, okay, so we make an ansatz for sigma and psi, because this works for all sigma and psi. So we make an ansatz, and the ansatz is the stupidest ansatz you could make. Sigma is a Fock state, a large Fock state, and psi is the simplest coherent thing that you can think about. So it's just a maximally coherent state between Fock state 0 and Fock state 1. Okay, right. So that's very simple. And okay, so you compute the coherent information for this case. It turns out it's just the difference of entropy of entropies of two probability distributions. So I don't know if you can see this, but these are probability distributions of an alphabet that goes from 0 to n+1. So it's an alphabet of size n+2. And okay, you get two probability distributions. You compute the entropy, take the difference. This is the coherent information. This is, for those of you who don't know, this is the entropy, the Shannon entropy of a probability distribution. And okay, so okay, the next thing to do is you plot it. You plot it for several values of n and lambda as a function of lambda. And you see when n becomes larger and larger, actually the spike in the coherent information goes closer and closer to 0 without actually going down. Actually goes a bit up. If you, I don't know if you can see this, but from n equal 2, 3, 4, it goes up, and actually goes always up, the spike. And besides going up, it also moves left. So for lambda very small, it's enough to make n very large, and you will get a positive quantum capacity. Okay, so that seems kind of the end of the proof. Of course, this is not a proof. It's just, we are just looking at the plots. This is no proof. And yeah, okay, I can make the plot for n equal 20, maybe for n equal 100. But of course, this is no proof that this thing will actually work. Yeah, okay, and right. I mean, but still, we can compute the probability distributions P and Q, right? So how hard can it be to prove that the difference of entropies is larger than a constant, right? Well, I mean, it turns out it's quite hard, because if you write down the explicit formula for P and Q, it's this nightmare here. Right, and then you have to compute the difference of entropies, not even the entropy of one, the difference of entropies. And at least for me, the resulting expression is analytically almost intractable. I mean, I wasn't able to see any way to lower bound this monster. Maybe there is one. I'm not saying that there isn't one, but I just wasn't able to see any way to lower bound this. But the plots are very clear, right? So there must exist a way to lower bound this, at least in principle. Okay, so and the idea is to prove that there is a majorization relation between these two probability distributions, two nightmarish probability distributions, however, are in a majorization relation. So what this means is that the P probability distribution is more disordered than Q in a precise mathematical sense. And this is why its entropy is larger than that of Q, because it's more disordered. And this precise mathematical sense is this, that you have an inequality between the sum of the kth largest P values of the P probability distribution and the kth largest values of the Q probability distribution. So this down arrow means that we have reordered the probability distributions in a descending order, right? They are sorted in a descending order. Okay, and so when this is true, when you have two probability vectors in a majorization relation, so it turns out that the difference of entropies is lower bounded by a quantity called the relative entropy between the two probability distributions. And oh God, I think I made a mistake. There is a typo here. You should have Q and P, not P and Q. Okay, but the main message is the same. So this paper by Ho and Verdu, quite a recent one, 10 years ago actually, they show that the difference of entropies can be lower bounded by the relative entropy distance between the two. And the relative entropy is the case. This expression, as again, the P and Q must be exchanged, but this is okay. This is a technical thing, but there is an expression that lower bounds this. So in particular, this is it's positive, as it should be, because P is more disordered than Q, but it's not only positive, it's larger than this quantity. And then we can combine this with Pinsker's inequality that gives you a lower bound on this in terms of the trace distance. Okay, so by combining Hohenverdu and Pinsker, you get a manageable lower bound for the difference in entropies. And then if you go back to the analytic form of the probability distributions that we saw before, you can actually, by inspection, you can see that this is bounded by a constant when lambda is in this range. And so that's the end of the proof. As I said, it's very, I mean, the technically kind of hard part is to prove this point 4, that this majorization relation holds, because of course you have to prove a bunch of inequalities, and that's it's complicated. Possibly it turns out to be complicated, but okay. After this, it's just I mean, it's complicated, it's cumbersome, but it's elementary, because you just have to prove a bunch of inequalities. Okay, they involve binomial factors, so there are a bit of polynomials to play around with, but that's it. Okay, so conclusions. So we look at quantum communication over general attenuators, and we studied the point 1/2, when the transmissivity is 1/2, and we identify the class of states for which the quantum capacity is 0, and this class of states includes the thermal states, the vacuum, and also convex combinations of Gaussian states, Fock diagonal states, kind of a general class of states for which this behavior is still true for lambda is equal to 1/2. But the main result is we identify this phenomenon of die-hard quantum communication, that is, that even when the transmissivity is very small, there are suitable states that can make the quantum capacity of a general attenuator larger than a constant, even when the transmissivity goes to 0, and even with an energy constraint. And with that, I thank you, and yes, thanks. See you around.